from the apex. If we were able to put a force directly on the center of mass, the tooth would move in a linear fashion without rotation, no tipping. If the force application is not through the center of mass, tipping is present. Now, how do we achieve this? We don't do periorbital surgery and put our orthodontic bracket on the root at the center of mass, but there are other strategies to accomplish this. Tipping movements are mainly with removable appliances that should be qualified as removable appliances, Holly type appliances with wires at the crown of the tooth and acrylic, similar to what you've done in the orthodontic project so far, in the active plate project. Translation is another word for bodily movement or linear movement. The root apex and crown move the same distance in the same direction with no rotation. But notice the force on the upper right, which is a pulling force, isn't just a point now, it's going through something. That something being an orthodontic bracket. And we'll show you how we use that orthodontic bracket to attempt to translate the tooth. Tendency to rotate is called a moment. Equal and opposite forces produce pure rotation, that's called a couple. And the way we can get close to linear motion is to use an orthodontic bracket. Piece of metal with a slot cut in it. In the course of orthodontic treatment, we start the alignment process with small round wires, progress to bigger round wires, then switch over to square or rectangular wires, and essentially fill the slot. Now we've got a so-called handle on the tooth, where it can move in a linear fashion, or bodily movement. Bodily movement is mainly with fixed appliances, not removable, although Invisalign type appliances can come a lot closer to limiting tipping than a Holly type appliance. And orthodontic brackets have slots cut in to them in different orientations, so that it isn't like you're taking a piece of wood and making one cut perpendicular to it. These cuts vary so that as the wire fills the slot, the teeth are moved in their ideal directions. So they're all not lined up like a picket fence. We talk about different kinds of forces now. Continuous heavy forces cause, as we've said before, hemorrhage, necrosis. Undermining resorption is present, not efficient. There's tissue reorganization after cleanup of the necrotic debris. This is damaging, not ideal. So questions on a quiz test might ask about the most ideal orthodontic forces. Continuous heavy wouldn't be the right answer. Let's look at another type of force. Light force, that's sounding better, but an intermittent light force. This allows recovery on one side. You have osteoid bone deposition or formation on the pressure side. But then you go and push the tooth again. You go to want to move the tooth again. And recall that Osteoid bone is resistant to resorption, resistant until calcium salts are deposited. So intermittent light forces are not efficient. That slows orthodontic tooth movement. So you don't want a stop and go on and off type of orthodontic force. Continuous light force, bingo. Now you have bone directly resorbed, you have minimal necrosis, minimal undermining resorption, no osteoid bone because you're given it time for the salts to deposit. This is ideal orthodontic tooth movement. Tissue reorganization takes time. On the level of the surface of the root, most of the surface of the root, periodontal fibers will rearrange fairly rapidly, about a month, 28 days in dog studies. They're very slow to reorganize at the alveolar crest. Basically, close to a year, 232 days, again in the dog study. The clinical extrapolation is that we don't give patients a retainer and tell them to throw it out after a month. We need long-term retention. We have a whole lecture, the last lecture, where we talk about retention, and we'll explore that more. The simplest spring is a cantilevered beam, a sort of diving board, if you will, okay? That's a simple spring. Stiffness is resistance to bending. Hooke's law. Deflection is proportional to load. We're not going to dwell on this, but deflection is proportional to load. The previous slide was talking about loading. Now we're talking about unloading. Return to an initial state. An ideal spring would release constant force, but we can accomplish nice forces with low stiffness springs. It's impossible to achieve constant force release, though. But you still can move teeth with springs, obviously. So orthodontic forces are through elastically deformed materials, wires, elastics, loading your absorbing energy, unloading your releasing energy. So you have a malocclusion, there's brackets or braces on the teeth, you have a flexible wire. On the upper, as you're facing the slide, the upper first bicuspid, you're engaging that wire into the bracket, which is loading. You let it go, and the wire will move the tooth into the arch form where we want it to be, a more ideal arch form. So we haven't loaded it yet, but then we do. The wire is deformed, and it goes back to its initial state. There's an almost endless variety of different springs and appliances that we use. Elasticity varies according to length, cross-section, that is it a round wire, a square, or a rectangular, and the material composition. So a lot of words here. I've never asked if stiffness varies inversely as the cube of length, or stiffness increases as a third power of diameter, but let's just simply look at this. So elasticity depends on length. We have a short diving board versus a long diving board, that simple spring. If you have a long diving board and you go to the end of it, it's going to bend more. The cross-sectional area. I think you can see from some wire bending that a round wire is going to be more flexible than, say, a heavier wire, a heavier square, or a rectangular wire. So you can get that just from what you already know about wires and materials, also material composition. We have a lot of different materials. Simply to say, nickel titanium, such as an alloy probably present in your eyeglasses, is more flexible than a stainless steel wire. So it varies with length, cross-section, and material composition. And we have charts that show stainless steel on the top is, say, much more rigid than a wire down the list. The elastic limit is that point on the stress-strain curve before it starts to curve. So a greater force than the elastic limit produces permanent deformation. We would like orthodontic springs to function within the elastic limit. The modulus of wire is another name for slope in the stress-strain curve. And the range of activation is this deflection up to the elastic limit, beyond which it starts to deform. Here's a high modulus wire, a steep slope, stiff wire, versus a flexible or low modulus wire, a flatter slope. Factors in spring design include loops and helices, which reduce stiffness. Again, we're putting loops and helices in to reduce forces and try to approach this ideal spring that will unload and move the tooth to where we want it to go. And there's many, many different spring designs that are present in many, many different orthodontic appliances. Thanks for your attention.